Hello everyone, in this lecture we are going to learn about pipe support, a stress analyst POV. Part 1 Theory. This is Part 1. Our flagship courses are Master Static Equipment Design, and PVE Light, ASME Section 8 Division 2, and Master Welded Storage Tank, as per API 650. We have curated courses to suit your learning needs. So do visit our learning platform for more details on scutoid.thinkific.com.
So now we are ready for analysis. So what is the first input that you get from the people for analysis? Now suppose I'm an analyst and I want to do the analysis of a line. So what do people feel that what should be my first input? Isometric. And isometric will have the lens, then it will have the material, it will have the various the designs of the various components, details, supports. So how the supports are marked on the isometrics? What is the information about the supports received on the isometric? So can before analysis, can a layout person say that, okay, this is my fixed point, this is my guide? Can the layout person say? So what information that we get on the isometric is the probable location of support on any line in the plant. So by various means. So for example, somebody may say that if this is my isometric and these are the crosses, what is meant by this is only a possible support location. The crosses mean that these are the possible support locations of the on the isometric. Now, it doesn't mean that every support has to be used. It is the prerogative of the analyst to decide on where to locate the support, which support is to be used, and he is also the person who will decide the type of support which is going to be used here. Now, whether a guide is to be used at this point, or a fixed point is to be used at this point, or whether this point should be used at all or no. I don't want to use this, and I will use directly the next point. This I'm not going to use. The location which is shown here is not going to be used. I'm going to use only the next point. So this is all decided by the person who is doing the analysis, and it is the responsibility of the stress person to do this. Now, once you have the isometric in hand, and if you directly start the analysis, it is most likely you are doing some lot of iteration of the analysis, because in one analysis you will not get the required results. You will keep on working on the isometrics for n number of iterations, n number of combinations of different solutions, and then you will come to the conclusion. But for a good designer, it is necessary for him to see first what are the chances of using that location of the support. What are the types of supports that are going to be better at this location, which will help me in doing the analysis very quickly. And so we must decide on the location and the type of supports. So there are some very simple rules which are going to be used for such a thing. So let us see some different very simple rules which will help us in doing this analysis. So our main task is going to be we need the longitudinal and lateral displacements. We'll use the longitudinal and lateral displacements to estimate the location in such a way that for a particular location, we know the displacement at any given point. So for example, let us see there is one small layout over here. We have an anchor or on the equipment, and we have a point where the line is taken to. Now my point A is a point which is having some interest in providing a support. Okay, so this support, I want to decide on what is the amount of expected displacement at this point. Now, in a simple case, what a layout engineer will do is he will simply connect the line, the blue direction, blue layout of the line. He will always ensure that a direct connection between the anchor and the point is done in a very simple way. But suppose you come across some interference in this, you will take a different path, and now the line because of this interference in this particular location, it is not possible to use this particular layout, and I have changed my layout from this. I have taken a rerouting and I have reached the point A. Okay. Now in the third case, suppose I find that this route is also not possible, and I take a completely different route, the one which is shown by the red line. Now, with all these different route locations because of the various impending interferences in the plant, what do you feel is the movement at point A possible? The displacement at point A due to the temperature, which is going to move in a definite direction, and with different routes being followed. What is your guess on what are the different types of movements expected at point A? In the blue line, whether the displacement is going to be less. In the green line, whether the displacement is going to be high. In the red line, the displacement is going to be further high. What is your take on this? Why blue is going to be higher than green, or why red is going to be very low? How is the expansion defined? What do you do? For example, at point A, I want to find the expansion. What do I do? Length, expansion. So, okay, length multiplied by the expansion coefficient, alpha into the length will give me the length. Now, how is the green different from the blue? Suppose let us take one by one. We have only blue and green. So how is blue different than green? Now, for example, now we have the point A is fixed by all the means we are reaching the point A. The displacement at point A we want to find out in this direction. So now in blue, it is directly that length L into alpha. Now in the green, that length is now divided into, say, L1 and L2. Now L2 is here. Now we have taken the L2 over here, and we have different lengths, say A and B here. Now here you will find that the expansion of A is going to be compensated by the expansion of B. The expansion of A is going to be compensated by the expansion of B because they are in the same direction, and they are going to expand in the same way, the same amount, and in equal and opposite direction. They are going to expand in equal and opposite direction. So do you agree with me that they are going to be compensating each other? The expansion of the green lake on the left-hand side and the expansion of the green lake on the right-hand side, they are going to be equal and opposite. The amount is same and the directions are going to be equal and opposite. So that means the amount of expansion at A is not going to matter at all as far as the two vertical legs of green are concerned. So what it matters is only L1 and L2, and my L1 and L2 is same as previous L, because L is nothing but L1 plus L2. L is nothing but L1 plus L2. So that means the deflection at A, if I follow, whether I follow the green path or the blue path, is going to be same. Do you agree with me? Whether I follow the green path or the blue path is going to be same, because the expansion of this lake in this direction is going to be compensated by expansion of this lake in this direction, and total expansion in the direction of this is going to be same, because this lake plus this lake is same as this total blue lake. If I make a statement now that whether I take a piping route of blue line or whether I take a piping route of partially blue and then green line, if I reach the same point A, my displacement at point A is same as the previous one. Now, can we apply the same logic to the red one also? Yes. Okay. So here we can see that now this expansion of this lake in this direction is going to be compensated by expansion of this lake in this direction. And this total length of red is nothing but a algebraic combination of this lake and this lake. That means this amount of expansion is here and this amount of expansion is in this direction. So effectively, it is nothing but the amount of expansion of the pipe in this direction. So the distance of point A is nothing but the large length of L minus short length of L, and which is nothing but the blue length pipe itself. So here I'm making a statement now that whatever layout that you follow, for reaching a particular location A, if you simply know that what is the shortest distance from the anchor point to the to this point of interest, and if you multiply by the expansion coefficient alpha, the displacement is going to be same whether you follow the blue route or you follow the green route or you follow the red route. Let me explain again. So if our point of interest is A, the amount of expansion, if you see in one direction, is going to be same whether we follow any different route, because all other routes for reaching the point A are going to be compensating each other in terms of the expansion which is taking place at that point. So clearly, let me just clarify again. So the expansion of this leg in this direction is going to be compensated by expansion of this leg in this direction, and the expansion of leg in this direction is going to be either the total blue length or the partial blue length and partial green length, which is totaling the total blue length. Lateral is not applicable because they are going to be compensating each other. They are one side, they are going to be in one direction, other side, they are going to be in other direction. So they are compensating. So here again, now this expansion is getting compensated by the expansion in this direction. So that is compensated. And the total expansion of this will be reduced by the expansion of this in this direction. And that is why the differential of this is nothing but the blue length, which is coming first. And we have a very clear understanding along the axis or the shortest distance. So we can easily say that we can conclude from this that for reaching a point A or finding out the displacement at any point of interest, it is not necessary to go along the route of the piping, but if you just locate the closest anchor in the system, the closest fixed point in the system, and if you find out what is the distance, the shortest distance between the point of interest and the anchor, simply you multiply by that with alpha, the expansion coefficient, and you will find what is the displacement at point A in the direction away from the anchor. Okay, so now this is the first simple logic that we have considered. Now there is one more simple trigonometric thing that we have here, construction. Now here we talked about the axial length of the axial displacement of the piping. Here we are talking about the lateral displacement of the piping, the lateral displacement of the piping in this direction. Now here we have a piping where the piping is fixed to the anchor, the blue pipe, and suppose we have another length of piping connected to other end. So for example, I have one layout of the piping in this direction. Now this will force the pipe to move laterally in this direction. Now we are talking about a triangle which is over here, and we find that at a distance B, if you see this triangle with an included angle theta, if you see this angle, now if at location B we have an expansion which is of y amount, then at any intermediate place we can simply find out what is the displacement in the lateral direction at any given intermediate point. So for example, at point A, if you see that it is going to be proportional because the included angle theta is going to be same. So if you simply put it in the equation, it will look like this: A upon B. So A is the distance of our interest point, intermediate interest point. B is the total length at which we know the amount of lateral expansion, Y. Y is the lateral expansion at distance B. And if at any intermediate point of A, suppose we want to find out what is the lateral displacement X, then we can simply write the equation A upon B is equal to X upon Y, because we know that the included angle theta is same in both the cases. Hope this is clear. So we talked about two logics, one for the axial displacement, another for the lateral displacement. In the second one, we are talking about the lateral displacement. Let me say it again. So suppose this line is connected with a pipe at the end also. Now because of this, there will be a deflection of the pipe in this direction of this pipe is going to see a lateral deflection by amount y. Okay, by amount y. Now, suppose we know in the geometry, now from the simple trigonometry, we can write down this equation that A upon B. So A is the point of interest where I want to find out any intermediate deflection in the lateral direction, and B is the point where I know that at this point B, my y displacement, lateral displacement is known. Then we can simply write this equation A upon B is equal to x upon y. Now, these two rules are going to help me in identifying and locating a support, a suitable support at that location. Now, remember that why we are doing this exercise is to decide how much is the expected displacement at a point of interest, which will decide on where to locate the support and which type of support. So whether my support location, now if without this, if you do this exercise of directly the analysis, then you are going to do a lot of more calculations as to where to locate the support, which is the type of support. So a simple exercise of this type is going to really help you in deciding the location of the support and the type of support.
Stay tuned for part 2, where we dive into the example. Launching of online live sessions on Pipe Stress Analysis and Caeser II course.
So we are going to study a lot of theory which goes into the understanding of the problems that are going to be there. So what are the different types of loads that are going to be analyzed in the system, what the concept of the expansion and the strain. Then a very simple example which stresses the importance of the stress analysis, why we must carry out a stress analysis, and if we neglect the stress analysis, what are the complications or what are the effects that are going to be there. Then we are going to consider the evaluation of the stresses on in the piping and the types of stresses which we studied today, some types of stresses which are of a very basic nature, and we didn't go into the much depth of how they are derived, why they are going to be occurring like that. So we are going to study that in depth in our session. So then we are going to have some introduction to the piping codes. So when we are going to study in depth one piping code, which is going to be the most important, that is 31.3 from the point of view of various industries that are going to be using this piping. And we are going to show you how the 31.3, 31.1 is similar or where it is going to be differing from 31.3. So we are going to see the similarities and the differences between the two, and we are going to study 31.3 in depth. So all the various chapters, right from 1 to 10, considering all the designs and materials, etc., we are going to see the essence of all these chapters which are going to be there. We are going to see the appendices, how the appendices, which are the important appendices for our day-to-day design works, and then how we are going to use that. We are going to do some calculations on the pipe thickness for internal pressure, then for external pressure, although it gives some reference to the ASME code, BPV code, but still for piping, there is going to be some limited application, and we are going to see only that part of the piping where we are going to use this external pressure thickness calculation. Then we are going to see the design check for pipe stub-in connection, RF pad requirements, miter thickness calculations, and various piping materials which are required in the industry for petrochemicals, chemical plants, and power plants. We are going to see why this code requirements are going to be there directly applicable to the stress analysis. So the piping code references with respect to the stress analysis and the requirements of the code compliance, the theories of failure, the understanding of the complex stresses. We saw the allowable stress range, then displacement stress range, and we just saw the equations. And we did not go into the details of the derivation of the equations or the concept of the calculations. And we are going to study in depth the displacement stress range, how those values of the bending stress and the torsional stress can be calculated, what is meant by the stress intensification factors, and how can we calculate with the help of the codes, various SIFs for stub-in connections, then flange connections, reducers, etc. So whatever different local changes are there in the stresses, how we are going to be considering that effect in the enhancement of the stresses which are generated in the piping system. Then after understanding this basic theory, we are going to study the various solutions which are going to be used for solving the problems related to the stresses, the strains, the higher loads on the in the piping system. So different solutions such as enhancing the flexibility, the application of the 4-bend, 6-bend loop, where 4-bend must be applied, where 6-bend cannot be used, or where 6-bend must be used. So all these studies we are going to make. Then what is the role of friction in the analysis? What is the concept of cold spring, the pre-stressing of the pipe, and how it is going to help in our analysis? Then limiting the values of the loads on the various equipment which are designed as per various standards like NEMA, API, or tank designs, the turbine designs, etc. That we are going to see the pump designs. So everything we are going to see, and how the limits can be achieved with the help of either directly the Caeser or manually also, whether we can make this use to check and limit those values within the range. The other loadings that we are going to see are the PSV reactions, that is direct force, the wind reaction, that is the pressure force, and the seismic load, that is the acceleration loading, which is going to be there. And we are going to study how they are going to affect the already displaced system, and what are the limits of the stresses applicable, and why the system should be made safe in those cases also, and how it is going to be different from the flexible system, because a normal analysis requires a system to be flexible, but whenever we have a seismic or wind loading, we need the system to be more rigid. So how to achieve a balance between those two requirements, and how to make the system safe for temperature as well as for loading, such as occasional loading such as seismic and wind. Okay, good. Next. So then we are going to study in depth the piping supports and the restraints. So the restraints and the supports are going to play a very important role in the design of the piping system, or the stress analysis of the piping system. So we are going to study the various types of supports from the construction point of view or the functional point of view, and how they are constructed at site. That also we are going to see. Then the use of the spring supports. Normal supports are going to be rigid supports, but occasionally we'll have to resort to some flexible supports like spring supports. And then in springs, there are two types. So which one to be used where, and how to make use of a vendor's catalog to select a required spring, because every time whatever the program gives, that is not going to be a final choice. And the user must be able to select springs on their own on few occasions, not every time, but sometimes there may be some applications where user must superimpose the requirement onto the software and design the springs accordingly. So we are going to study all such applications for the springs and the supports. Then going on to the Caesar, we are going to see the how to develop the Caesar modeling, how to model the basic pipes and various components of the pipes, like T's and branch connections, reducers, walls, specialties, equipment modeling, the concept of connecting nodes, restraint modeling, and application of the wind loading, seismic loading, PSV forces, the concept of initial displacements when the tank settlement occurs. Most of you are aware of the tank settlements. So how to take the effect of the tank settlement into the analysis, that we are going to study. Then we are going to study the for modeling. There are various parameters which are going to be set before you really start on the modeling. So how to set the various parameters? There are hundreds of parameters which you need to study, and then only the actual modeling or the analysis starts. So we are going to study all those control parameters, the study, and then various effects of those control parameters, and how to change the drawing in the form of isometric on your table into the isometric, which is understandable by the software, that is the Caesar. So for that, we have certain method of node numbering, and to generate the model into the Caesar. That also we are going to see. We are going to see various options which are given by the software, such as copy, duplicate model, rotate model, delete the unwanted portion, copy from the previous project if there is some similar system. Then study some systems with the various temperature pressure effects. For example, there are various systems in the piping which are going to work in different ways of operations. So suppose we have some 4 or 5 pipes interconnected, then one pipe may be working at one time, another pipe may be not working at that time. So how to analyze, how to understand the operations of the system, and how to conclude this system's various temperature, pressure, and changes into the system, so that when you analyze the system, you will have only one solution. We cannot have different solutions for different operating conditions, and we must find out one solution for all the operating conditions. And we are going to study two such temperature cases. One is 2 temperature case, another is 3 temperature cases, which will make it abundantly clear to work on many more such systems. The software has got a facility to work up to 9 temperature pressure cases for one system. So we are going to study how to apply that technique to the analysis. Then we are going to study the modeling of the supports, the bellows. We are going to study make the flange checks. For example, a flange may also lead to a failure, because whenever the flange is there, it is supposed to be the most weakest joint in a piping system. And when heavy stresses are transmitting through the flange connections, then the flanges may open up, and the software has got a facility to find out whether there are any such cases. And we are going to study the flange checks. Then the nozzle flexibility is there, which we can superimpose onto the system to take advantage of the flexibility of nozzle connection with the equipment. Then we are going to study the supporting from the equipment, because there are going to be many such equipment which are going to be used. For example, tall columns, where many of the piping which is dropping from the top to the bottom, it is supported from the column itself. So that effect is going to be totally different than the normal supports which are going to be resting rigidly on the structures. So we are going to study that, and then we are going to have a lot of advanced features also that we are going to study. For example, natural frequency calculation, then dynamic model analysis for pulsation, then dynamic analysis, seismic response spectrum analysis, force response spectrum analysis for slug and plug applications. So we are going to study such advanced cases also, which are generally not available in the industry for anybody to study. That we are going to cover that part also in our Caeser applications.
If you learn in community with a trainer who is guiding you, and it's a time bound. So 3 things will definitely help you to achieve. Okay. Achieve the result very fast, to accelerate your learnings. Okay. And apart from that, if you see 60% of overall project efforts comes from piping. Okay. 60 to 70% manpower is in piping. Okay. So it's definitely in very, very huge demand. And stress analysis among the piping group, almost 40% of the man hour goes into stress analysis. Now, okay, course will also talk about the layout related and overview of the course, which will definitely help you. Specifications, okay, stress analysis definitely in detail. So these things are very, very important for you to understand how piping behaves and how you will be able to work in this domain. Okay. So it's definitely covering 90% of your requirement of critical analysis. Whenever you are doing stress analysis or working as a role of stress analysis engineer, almost 90% of day-to-day work we are going to cover in this course. So that is really, really amazing. Now there are a few things like super advanced topic, which may be used very little, but if you know, that will give you an edge. Okay, because those things very few people know about that. So definitely it's very, very important, and less data is also available on the net. So yes, very important. Okay, and definitely we will to cover refineries, petrochemical, power plants, all the different industries. Okay, great. So very good opportunity to upgrade yourself. So definitely, why not? Okay. So just to summarize how we are going to conduct this, it will be theory like we conducted right now, and it will follow with examples, live examples. We'll be doing the calculation together, and then software. So we'll be doing the same operation in the software. Okay, doing lots of modeling, analysis using Caeser II. The classroom will be live sessions, okay, online like we are doing right now. The duration will be 55 to 60 at least. Okay, it will run for 5 to 6 months. The course is starting from 3rd June. So still we have a month's time. Okay. And 8:30 p.m. same time when we are doing it right now. If the class will be conducted every Tuesday and Thursday. Okay. So 2 days in a week, the class will be conducted. For some reason, if you miss out any class or you want to revise the concepts, okay, so this is a very important part. So it should not happen that you attended the class and then it's gone. Okay. So we are recording every class, editing and making it available as a e-learning course for you so that you can view it even 1 year after you have attended the training program. So course duration after the session is ended. So if you think from the starting, so 1.6 years it will be available for you. Okay. And lots of study material and definitely test will be conducted so that we are checking our progress. 1 year support with live Q&A will be provided once the course has ended. Okay. So till 1 year, whatever queries you are getting in your day-to-day work life, that will be solved with live sessions. Okay. And there will be WhatsApp community, which will be accessible for you for lifetime. You'll become part of that. You can ask questions. Trainer will be there. He'll be answering your question. You guys can also participate in the discussion. So community support so that learning does not end. Okay. And you have somewhere to ask your doubts. Okay.
For in-depth training and to learn more about these courses, register with the link in the description.